so going back to the pressure volume graphs we were looking at last time. Volume versus pressure. We were taking a look at isobaric and isochoric processes, constant volume versus constant pressure. And continuing on the constant pressure process, I think there's something very important we can get out of that. Pressure, let's say the pressure is constant, but the volume is changing from some initial value to some final value. You've got some initial volume and pressure and a final volume with the same pressure. And we're just going through this process from one to the other. In that process, let's take a look at what's happening in each piece of that first law of thermodynamics. And thermodynamics literally just means the study of how heat moves around. Thermo in the sense of temperature or heat flow, dynamics meaning in motion. So we're really just talking about how thermal energy and other forms of energy move around in a system. First law of thermodynamics, just conservation of energy, exactly as we've been seeing, focusing specifically on internal energy, which in this case, we're treating as what type of energy? What's the only type of energy we really care about here? Yeah, thermal energy. And of course, it also usually should include bond energy, chemical energy, nuclear energy, but thermal energy is the only one that's changing in this context, a gas in a container. So thermal energy is the only one we really care about. And generally in a graph like this, in any process where we know something about where it starts, where it ends, and what's going on in between, usually what we're trying to find is how much does the energy change from start to finish? How much of that was accomplished by heat? How much of that was accomplished by work? How does it split up? And in a case like this, how would you figure out the change in energy? Could you get that information from the graph? Yeah, one way we could do this, because the usual indicator is temperature, so you could use PV equals nRT. So, this is a different color. So one way of finding delta U is you could use PV equals nRT to find, because you know initial pressure and volume and final pressure and volume. You could use PV equals nRT to find T initial and T final. Then use delta E thermal equals heat capacity times delta temperature, where heat capacity might be mass times specific heat, or number of moles times molar specific heat, or whatever formula you want for heat capacity. And yeah, you could probably more easily use the formula delta E thermal equals 1/2 times number of modes. Number of modes over 2 times nR delta T. So this is the formula we got from the microscopic analysis of thermal energy, looking into what's going on in the behavior of the individual molecules. Half the number of modes times number of moles, times ideal gas constant times the change in temperature. And most conveniently, since we're specifically talking about a gas, what could nR delta T be replaced by? Yeah, nRT is PV. So nR delta T is delta PV. And that's delta the whole thing in the sense of final pressure times final volume minus initial pressure times initial volume. So we could replace the nR delta T with just delta PV and we get delta E thermal, which in this context is delta U, equals number of modes over 2 times just delta PV. And this is an extremely convenient formula for thermal energy because it's referring to pressure and volume, which are directly shown on this graph. We don't even need to know what the temperature is. Sometimes it can be useful to find the temperature anyway, which you can do using pressure and volume at each point. But you don't really need the temperature. If all you care about is the change in energy, you can use this formula, invoking just the initial pressure and volume, the final pressure and volume, and you'd also have to know the number of modes. Or alternatively, maybe you know the delta E thermal, or you can find it by other means. Maybe you know the amount of heat and work. And then you can solve for number of modes, which tells you some useful information about what type of gas this is. But generally, this is the formula we're going to be using to relate delta U, this left side of the equation, with the pressure volume graph. And note that since this is a delta of a state function, that only depends on what aspects of the graph. What are the only parts of the graph we need to care about when calculating delta U? Yeah, we only have to care about initial and final states. The stuff going on in between, that's the process, that's going to heavily influence the values of Q and W. But delta, any state function, all we have to care about is the initial and final values. That's where the delta PV comes in. So that you can find just using initial and final values. Initial pressure and volume, final pressure and volume. As for the other side of the equation, heat and work are processes, so they're going to depend on the path taken. If you take this path, you're going to get a certain value of heat and a certain value of work that add up to this delta U. If you take a different path, let's say you go up to a higher pressure, expand the volume at that higher pressure, and then drop the pressure, you're still starting at the same point, you're still ending at the same point, so you still have the same delta U as before. But the heat and work are going to be different values. They just still add up to the same delta U. So if you take any two processes that all start at the same point and all end at the same point, all these processes I'm drawing in here, all these processes involve the same overall change in energy. They're just split up into different amounts of heat and work, but those heat and work still add up to the same delta U. And in a case like this, let's say for simplicity, it is isobaric, constant pressure the whole time. In that case, how would you calculate, could you find either one of these from just the graph? Yeah, you can find work from the graph alone. And how do you calculate work? Right, work is just the area under the curve. If you just drop lines straight down to the axis from initial and final points, the area under the curve, from the curve all the way down to the axis, that's the amount of work. And to formalize that, mathematically, how do we write out the area under the curve? What notation from calculus do we use for that? Yeah, this is literally just an integral. Specifically, the integral of since the output, the y value here is pressure, we're treating pressure as the function. Pressure is a function of volume. So for each volume, there's a value of pressure, meaning we're integrating pressure with respect to volume from some initial volume to some final volume. Also, we got to be careful about sign. In this case, what's happening to the volume as time passes? Volume's increasing, so the gas is expanding. Does that mean work is entering or leaving? Yeah. When the gas expands, work is leaving the system because the gas is pushing outwards on the walls. So we have to treat work as a negative value. If work is leaving the system, then we say work is a negative value. We still write this as heat plus work every single time. It's just that the value of work is a negative number. And so to account for that, we say work is opposite of integral of P dV. Because integral, if you're integrating from left to right, you get a positive result, but we want a negative value for work. If you're integrating from right to left, if you're compressing the gas, the integral gives you a negative result. Integrating from right to left gives you a negative value. But we want a positive value because if you're compressing the gas, you're doing work to it. Work is entering the gas, so we should treat that as a positive value. So if we're integrating from right to left, the integral is going to be negative. This negative sign flips that to make it a positive amount of work. Or more generally, you could just find the area geometrically if it's easy to work with shape like rectangles or triangles or trapezoids, and ask yourself, is the gas expanding or contracting, and then attach the appropriate sign to it manually. But if you actually have a formula for pressure in terms of volume, if you have an equation for that function, you could integrate that, apply a negative sign, and that tells you the amount of work. Any questions on work so far? And for the special case of constant pressure, if pressure is constant, the area becomes very easy, because what shape do we get if the pressure is constant? Yeah, we just get this rectangle. And how do you find it? I wouldn't necessarily say a square because there's no guarantee that the width and height are the same values. In fact, since the width and height are measuring different quantities, we're measuring cubic meters worth of volume versus pascals worth of pressure, we can't really compare the distances at all. But we can certainly find the area of the rectangle by using what calculation? Yeah, width times height. In this case, the width is the change in volume. Note that the width is not just volume, the width is the change in volume. But the height is not the change in pressure, the height is the pressure. So in the case of the constant pressure process, height is pressure, width is change in volume. So the work is pressure times change in volume. Also, an increase in volume means work is leaving, so we're going to need a negative sign here. Like in this case, volume's increasing, so delta V is positive, but we want the work to be a negative value. So work is the opposite of pressure times change in volume. And this is specifically for the constant pressure case. More generally, it's the area under the curve, but if the pressure is constant, that area becomes a very straightforward rectangle. So our first law becomes, we can write out still delta U is delta U. Heat, maybe we don't know, but we know plus work is minus P delta V. So we get a much more specific version of the first law of thermodynamics if the pressure is constant. Any questions on that so far? So to recap, you can find delta U from the graph by looking at the initial value and final value and using this formula or some variant of that, as long as you know the number of modes. You can find work from the graph just based on the area under that path. And then for heat, does heat show up on the graph? Not directly. But if you know everything else in the equation, how would you solve for heat? If you know delta U from the initial and final points, and you know work from the area under the curve, yeah, all you've got to do is subtract W. So heat, once you know everything else, you can just solve algebraically. Heat is delta U minus work, in the sense that the delta U is accomplished partly by heat and partly by work. If you subtract work, you're figuring out what's left. What is the amount that's done by heat instead? So in the end result, all three of these can be found from the graph. Delta U directly from the initial and final values, work directly from the area under the curve, and heat indirectly by solving algebraically once you found the other two. Or alternatively, maybe heat is given. In some situations, maybe they might tell you exactly how much heat is applied, and you can find work as area under the curve, and maybe the number of modes is unknown. So if you know everything else in this equation except number of modes, area under the curve, maybe heat is given, and pressure and volume are known from the graph, you could solve that for number of modes algebraically, and that gives you some information about what type of gas it is. For example, let's say you solve for number of modes and find that the number of modes is 5. If there's exactly 5 modes per particle, what does that tell you? Diatomic? It could be diatomic. and definitely no vibrational modes. It doesn't necessarily have to be diatomic though, because if you look at 5 modes, diatomic is certainly a possibility. But if we account for those modes, what modes do we have to include, no matter what type of particle it is? Yeah, we've got to include 3 translational modes because the particle is able to move in 3 dimensions. There's 2 left over unaccounted for, so what are those other 2 modes? Yeah, 2 rotational modes. And there being 2 rotational modes is really the key here. 2 rotational modes might be diatomic, but it could be any number of atoms in the molecule. The important thing about 2 rotational modes, what information does that give us? Yeah, it's linear in shape. It might be diatomic, might be triatomic, tetraatomic, pentatomic. Doesn't really matter how many atoms are in the molecule. The important thing is only 2 rotational modes tells us the shape is linear. All the atoms in the molecule are arranged in a straight line. Because if there was any bend in it or any one atom off that line, we would expect 3 rotational modes. And this is, of course, assuming all the rotational modes are active. If this is kind of cold, maybe it's nonlinear, but only some of the rotational modes are active. And then this is, of course, also assuming that the vibrational modes are frozen out. If it was at a hotter temperature, we'd expect more modes to be active because you'd have 3 translational, 2 rotational, and also who knows how many internal vibrational modes, depending on how big the molecule is, how many atoms. Any other questions on that so far? All right, let's see if we can look into how this applies to the idea of heat capacity. Because we've been briefly seeing ideas like the heat capacity is different if you're holding the volume constant versus if you're holding the pressure constant. The reason for that has to do with this idea of solving for heat and getting delta U minus W. In fact, the way we define heat capacity in the first place, the definition of heat capacity is a little bit different from the way we've been treating it at the beginning of the quarter. The actual definition of heat capacity is the ratio of heat over delta temperature. The idea is you add some heat to an object and you find that the temperature increases. You add more heat, temperature increases more. And if you measure this repeatedly, you find that there's a proportionality between the heat added or removed, could go either direction. Heat added or removed is proportional to the delta temperature. If 2 things are proportional, that means one of them equals something times the other. And we call that something the heat capacity. So heat capacity is the constant proportionality between heat added or removed versus change in temperature. Like let's say you add 100 joules of heat and you find the temperature changes by 3 Kelvin. 100 divided by 3 would be 33 1/3, so that would be the heat capacity. How much energy it takes per Kelvin of temperature change. So we can write that as a ratio. Heat capacity is the ratio of heat added or removed versus change in temperature as a result. And it's very useful to think of that as a unit rate of change. It's the heat capacity is the cost of changing the temperature by 1 unit. Like if we say the heat capacity is 50 joules per Kelvin, we're saying it costs 50 joules of energy to change the heat capacity, to change the temperature by 1 Kelvin. And since this is a delta temperature, it could be Celsius or Kelvin, doesn't make a difference, as long as you're consistent about it. But the amount of heat is really going to matter based on, or is going to differ based on whether we're keeping the volume constant or the pressure constant or somewhere in between. So let's take a look at both of those cases, constant volume and constant pressure. First of all, let's start with constant volume. An isochoric process. Volume is constant. If we go back to the first law of thermodynamics, delta U equals Q plus W. But for an isochoric process, what do we know about W? How much work is done if there's no change in volume? Yeah, 0. If you've got a gas in a rigid walled box or with a piston that's locked in place and can't move, if nothing's moving, there's no work being done. Work requires some sort of motion. So in isochoric, there's no work at all. Work is 0. So that means delta U and Q are the same thing. And this is basically what we were looking at the beginning of the quarter, when we were just treating heat capacity as delta E thermal over delta T. Because if you substitute Q for W, you can say heat capacity equals Q over delta T. If there's no work, we can just replace Q with delta U. And we're specifically going to call this CV, the heat capacity at constant volume. So that's what the subscript means. The subscript means the variable we're assuming is staying the same. So when you have a gas at constant volume and you measure the heat capacity, we're still defining it as heat over change in temperature. But if there's no work, that's the same as change in energy over change in temperature, because the heat is the change in energy. And what type of energy are we really talking about again? Yeah. In this context, if the only thing changing is the temperature, we're not looking at any phase changes or chemical reactions or anything, delta U is just delta E thermal. And we have a formula for that, right? If we just substitute in our microscopic formula for delta E thermal, the number of modes over 2 times N times R times delta T, that's our microscopic basis formula for delta E thermal. But then we're dividing that by delta temperature to get the heat capacity. What happens when we divide those? Yeah, delta T cancels out. Meaning that the constant volume heat capacity is just N times R times number of moles over 2. So this is a very useful expression for the heat capacity at constant volume. All you need to know is how many modes and how much of the substance. In fact, we could even take this a step further. We can standardize this by what would be a very convenient standard number of moles to use. 1. If we just say, let's standardize this to exactly 1 mole, we just get 1 times R times number of moles over 2. In other words, R times number of moles over 2. So that's the heat capacity of exactly 1 mole, which we usually call little c Vm. And that's usually called the molar specific heat, the constant volume molar specific heat. It's sometimes also called molar heat capacity because it is just the heat capacity of 1 mole. But it's a specific heat in the sense that we've standardized it to 1 unit. And this means it's extremely predictable. The specific heat, the molar specific heat, the heat capacity of exactly 1 mole at constant volume is always going to be R over 2 times number of modes. So number of modes is the only thing that matters. If you know the number of modes, like for instance, let's say we're looking at that linear gas at room temperature. Its constant volume molar specific heat should be R over 2 times, how many modes was that? 5 modes. 5 over 2 is 2.5, so 2.5 times R. R is about 8.3-ish, so 2.5 times 8.3 should tell you the constant volume molar specific heat of any linear gas. And again, this is just to make the whole thing very predictable, that we can predict what heat capacity we should expect per mole if the gas is at constant volume and we know how many modes it has. Or in reverse, you can measure the heat capacity by doing an experiment at constant volume. Just put this gas in a rigid walled box, add some heat, measure how much the temperature changes, and divide. That tells you the constant volume heat capacity, and then you can solve for number of modes, and that gives you some information about the type of gas it is, how many modes are active, and therefore you can infer what shape it is. And by performing this experiment repeatedly at different temperatures, you can figure out how the number of modes changes at different temperatures and get information about when or what temperature, how hot does it have to be to activate the vibrational modes. And so when you're looking at how many vibrational modes are active at what temperatures, typically that's done by looking at a graph of temperature versus Cvm. And that's going to be gradually rising because as you increase temperature, you activate more modes. More modes per particle means a higher heat capacity. So if you measure the heat capacity at various different temperatures and plot those data points on a graph and connect them with this smooth curve, then you get a curve describing how the number of modes changes as the temperature increases. Any questions on that so far? So that's all the constant volume stuff. And this is basically the heat capacity we were looking at the beginning of the quarter, the molar specific heats we were looking up on a data table. That's specifically talking about the heat capacity at constant volume, in which case we can assume that heat and delta E thermal are synonymous. If we're looking at an isobaric process though, if we're allowing volume to change, but we're keeping the pressure constant, things are going to be different. Isobaric, so pressure is constant. And in that case, if pressure is constant, what's our formula for work? Yeah, P delta V. And also because of the direction, there's going to be a negative associated with it as well. So work is negative P delta V. If we now write out our first law of thermodynamics, delta U equals heat plus work, we can now replace work with negative P delta V instead of replacing it with 0. And if you solve that for heat, you can just add P delta V to both sides. So heat is delta U, which we can write as delta E thermal, plus P delta V. So this is a formula we can use for heat now. Anytime we're dealing with a constant pressure process, allowing the volume to change but keeping the pressure the same, heat can be replaced with delta E thermal plus P delta V. And this is a very interesting idea here, I think, that in the constant volume case, heat is delta E thermal. All the heat you add goes into increasing the thermal energy. But here, some of the heat you add goes into changing the thermal energy, and some of the heat goes into changing what instead? Volume. So this is a less efficient process. If your goal is adding heat and making the temperature go up, constant pressure is less efficient. Constant volume, all the heat you add goes into raising the thermal energy. Constant pressure, some of the heat goes into raising the thermal energy. Some of the heat goes into making the gas expand. Some of the heat is, you might say, lost as work. In fact, you could even see this with conservation of energy. The energy we care about is thermal energy. We're treating this as an open system because you're dealing with heat and work. You're adding heat, lots of heat. What does that do to the thermal energy? Yeah, thermal energy is going to increase as the temperature goes up. And based on the ideal gas equation, we've just increased the temperature. So what else has to happen to balance that out? Yeah, the volume is going to increase. The pressure can't because we're assuming this is constant pressure. So raising the temperature makes the gas expand. But as the volume increases, what's happening with work there? Is work entering or leaving or nothing? Yeah, gas expanding means work is leaving the system. So a constant pressure process is going to look like this. You're adding heat to raise the temperature, but also as the gas expands, work is leaving the system. So you've got to add a lot of heat. You've got to add extra heat because you're not only adding enough heat to raise the temperature, you also need to add enough heat to balance out the lost energy due to the work leaving. So that's what I mean when I say this process is less efficient. You're adding heat to raise the temperature, but you have to add extra heat to account for the energy loss as the gas expands. So we should expect a more difficult, if we're trying to raise the temperature, we should expect this to be more difficult. That means that we should expect the heat capacity to be larger because the heat capacity represents how difficult it is to raise the temperature. Any questions on that conceptually so far? Then let's see if we can work this out algebraically as well and get an actual formula for constant pressure heat capacity. If we make this substitution, again, going back to the definition of heat capacity, heat capacity is Q over change in temperature. But we now know heat can be replaced with delta E thermal plus P delta V. That is delta U minus work, all divided by delta temperature. And since we made that substitution, we should mark this as specifically the constant pressure heat capacity, as opposed to constant volume or anything else. We could then split that up. Since this is just a couple of things divided by delta temperature, we could just distribute that division and say this is delta E thermal over delta temperature, plus this extra term, P delta V over delta temperature. But where have you just seen delta E thermal over delta temperature? Yeah, that is exactly CV. CV is delta E thermal over delta temperature. So we can make a substitution. CP then is going to be CV plus this extra term. What this tells us is, since this term, if you increase the temperature, you're expanding the volume. So delta T and delta V are both positive or both negative. That means this term is going to be a positive. So constant pressure heat capacity is always going to be constant volume heat capacity plus a little bit extra. CP is going to be larger. It's more difficult to change the temperature at constant pressure than it is at constant volume. And we can take this one step further as well, because what other equation do we have that relates P, V, and T? Yeah, going back to the ideal gas law, we know PV equals nRT. If we apply a delta to both sides, we're specifically assuming isobaric, so pressure is constant. The only thing changing on the left side is volume. So P times delta V. And on the right side, of course, the only thing changing is temperature. So N and R can be treated as constants. That means if we see P times delta V, which we do right here, we can replace that with NR delta T. Then we're dividing that by delta T, and what happens? Yeah, delta T is canceled out. We're left with just NR. So this tells us how heat capacity at constant pressure is related to heat capacity at constant volume. It's just the constant volume heat capacity plus an extra term, and we now know that extra term is NR. So that's the little bit extra, number of moles times the ideal gas constant. Or what's a good standardized number of moles to use? So if we look at standardizing this for 1 mole, the molar constant pressure heat capacity, or molar specific heat at constant pressure, is the molar specific heat at constant volume plus 1R. So this is a very convenient and tidy and elegant way that these quantities are tied together. the molar specific heat at constant volume is always number of moles times R over 2. The molar specific heat at constant pressure is that much plus an extra R. In fact, you could even fill this in. Number of moles over 2 times R, that's the CVM, plus an extra R. You just divide each side of the equation by 1 mole. It's more that we're just substituting. We're replacing N with 1 mole. Because this equation is true for any value of N. But in this case, we're specifically saying what happens if N is exactly 1. You could also think of it as dividing both sides by N. Constant pressure, or the heat capacity divided by number of moles, is the molar specific heat. I usually just think of it as assume the number of moles is exactly 1. So as to standardize it to a convenient single unit measurement. And that's often the case. In many situations, you have some quantity that varies with how much of the substance there is. So you say, what if there's exactly 1 unit of the substance to standardize it? And that's the specific heat per kilogram or the specific heat per mole. Or like even things like density. If you just take the mass divided by the volume, you get the number of kilograms per cubic meter of space. So density is also a unit ratio sort of thing, the amount per unit of volume. Any other questions on how those are related? So again, looking at the example of, let's say, the diatomic gas. Assuming we're close to room temperature, so the internal vibrational modes are frozen out, there's 5 modes per particle. So CVM, you can just take R times 5 over 2, or 2.5 R. If we now wanted CPM, we just take that value and add R to it. So what's 2.5 R plus another R? Yeah, we just get 3.5 R. So 3.5 times about 8.31 joules per Kelvin mole. So as long as you know the number of modes, both the molar specific heat at constant volume and the molar specific heat at constant pressure are very predictable. You can just use number of modes times R over 2 for the constant volume molar specific heat, and that value plus another R to get the constant pressure specific heat. And we know constant pressure has to be larger because if it's constant pressure, the volume's able to change. That means you're losing work as the gas expands. So you have to add more heat to get the same temperature change. More difficulty, because you have to add more heat, means a larger heat capacity. Any other questions on heat capacity? All right, then let's see if we have time for one quick example on pressure volume graph with some actual numerical calculations. See if we can actually find the amount of heat, the amount of work, all that stuff. All right, so here's our process. The gas starts at 3 cubic meters of pressure of volume, 5 kilopascals of pressure, and then changes until it's 10 cubic meters of volume, so it's expanding, and only 2 kilopascals of pressure, so it's at a lower pressure. And if we write out the first law of thermodynamics, delta U equals Q plus W, let's say what we're trying to find is the value of all three of these terms. We want to know exactly what each one of those is. And we can find all of those using the process we discussed earlier. Delta U we can find from the initial and final points. Work we can find based on the path. And heat we can find algebraically after we find the other two. So let's start with delta U. In other words, delta E thermal. We can use our usual microscopic formula for that, and our delta T times number of modes over 2. But let's say we don't want to have to worry about finding the temperature. What could we replace nR delta T with? Yeah, we can replace nRT with PV. So nR delta T can be replaced with delta PV times number of modes over 2. And if pressure was constant, we could pull that out of the delta and get P times delta V. Or if volume was constant, we could pull that out of the delta and get V times delta P. In this case, though, they're both changing. So we have to leave this as delta the whole thing. In other words, expanding it out, we would write delta PV as P final times V final minus P initial times V initial. And then what information would we need to know for number of modes? Because all the pressure and volume stuff we can just read directly off the dots. But what information do we need to know to get the number of modes? Yeah, we need to know what type of gas it is. In this case, let's say it's monoatomic gas. Let's say we already know that. Maybe it's a noble gas, helium or argon or whatever. For a noble gas, monoatomic gas, how many modes should we expect? Yeah, it's got the 3 translational modes and that's it. So let's plug in those values. We know the final pressure and final volume. Final times final, so that's 10 cubic meters times 2 kilopascals. So that's 20 cubic meters times kilopascals. Minus initial, that's 3 times 5. So that's 15 cubic meters times kilopascals, multiplied by 3/2. 20 minus 15 is going to be 5. We also need to multiply by 3/2. And as for the units, we're going to look into what pascals means in a lot more detail in 7b when we look into fluid flow. But for now, I'm going to say Pascal can be written as joules per cubic meter, or as newtons per square meter. Newtons is the unit of force. Pressure is a force over an area. So pascals is defined as newtons per square meter. It turns out that's also equal to joules over cubic meters, energy per unit of volume. So if we take pascals and multiply by cubic meters, the cubic meters are just going to cancel out. In general, pascals times cubic meters is joules. But we've also got this kilo here, kilopascals. So that's going to be kilojoules. So that's how the units would work out. 5 over 2 would be 2.5, times 3 would be 7.5. So 7.5 kilojoules. That's the delta U. And that's positive. What does that positive suggest to you? If delta U is positive, what's the gas doing? What's the indicator for delta E thermal? Yeah, if the thermal energy is increasing, that means the temperature is increasing. So this process from here to here, this represents an increase in temperature. And you can actually tell that just by looking at the pressure times volume. Ignoring number of modes for a moment, P times V equals nRT. we know N and R are constants. So if the total pressure times volume is increasing, then temperature is increasing. At the initial location, pressure times volume is 3 times 5, that's 15. In the final situation, pressure times volume is 20. We've increased the value of P times V, so we've increased the temperature. This location is higher temperature than this location. Any questions on the delta energy so far? And then what's the next thing we can find from the graph? Yeah, we can figure out the amount of work. And that's just going to be area under the curve. So what I usually do is just draw from the initial point straight down to the axis, from the final point straight down to the axis. We're looking for the total area from the curve all the way down to the axis. That's a trapezoid in this case. So if you happen to remember a trapezoid area formula, you could use that. If not, what easier shapes could you split this into? Yeah, any trapezoid. In fact, anytime the process is just a straight diagonal line, you can almost split that into a rectangle and a triangle. Rectangle is just going to be base times height. So that's going to be, height is 2 kilopascals. From 3 to 10, the width is 7. So 14. And that's again going to be kilojoules. Triangle, how do you find a triangle's area? Yeah, 1/2 times the base times the height. The base is still 7. The height from 2 to 5 would be 3 kilopascals. So 3 times 7 would be 21. Half of 3 times 7 would be 10.5. Add those together to get the total area, 24.5. And again, we're multiplying cubic meters times kilopascals, so we get kilojoules. And it looks like the volume is expanding. So would you treat this as a positive amount of work or a negative amount of work? Yeah, this is a negative amount of work. So we know work is negative 24.5 kilojoules. And at that point, the only unknown left is heat, which we can easily find by doing what? Yeah, delta U minus W, that's going to be 7.5 minus 24.5 becomes plus 24.5. So that's 32, I think. Positive 32 kilojoules. That means in order to make this process happen, you have to add 32 kilojoules of heat and allow the gas to expand, allowing 24.5 kilojoules of work to leave. The difference between the heat entering and the work leaving is the energy that stays in the system as thermal energy, making the temperature increase. But this is really the main goal of a lot of situations like this. Given a graph of this sort, figure out every term in the first law of thermodynamics. How much is the energy changing? How much of that was heat flow? How much of that was work done? Or alternatively, maybe you know some of these and you're trying to find other information, like maybe you don't know the number of modes, but you can solve for it. But it all is tied together with the first law of thermodynamics and the ideal gas law. Those are really the key ideas that bind all this together, also combined with our microscopic formula for thermal energy and interpreting this graph. Any other questions on that?
Can you explain one more time how you knew the temperature was increasing?
Yeah, going back to the ideal gas law, ignoring the N times R, because that's a constant anyway, temperature is directly proportional to pressure times volume. If pressure times volume overall increases, then the temperature is increasing. Or if pressure times volume overall decreases, then the temperature is getting colder. So if we just calculate pressure times volume at the beginning and pressure times volume at the end and compare those, the value of pressure times volume has increased from 15 to 20. If this value has increased, then this value has increased also. So the temperature is rising.
Thank you.
Mm-hmm. All right, have a good weekend, and feel free to make some practice problems if you want to. If you just want to just get some more practice with that, I was literally just drawing the axes, marking some points, some values on the axes, and just draw a straight line path. Good way to get some extra practice and develop more of an intuition for how these things work. So try just making up some practice problems and running through them. Just make a graph, choose what type of gas it is, and try finding all three terms in the first law of thermodynamics. Give it a try. Feel free to email me if you have any questions, and I will see you next time.